prime of x is limit of h approaching 0 of, so whenever I say definition of the derivative, this is the definition, okay, not the power rule. We'll get to power rule today, finally, but still, definition means this. Then it becomes 1 over x plus h squared a. So far, so good. Now, this is equal to limit of h approaching 0 of common denominator as always. So this is a common denominator. So we have x minus. Now, can I just square this while I'm at it? Or would that be too much algebra? It's a square. And then h, 1 over h, we can just stick it in here, right? With me so far? If you have questions, now is the time. Okay. Then x squared can, excuse me, x cubed squared cancels. I'm gonna not skip the line and write this down, but you may skip this line. Right? And then h factors and cancels. So negative 2x minus h over x plus h squared x squared. You may skip this line and go directly there. Good. Now we take the limit and h dies. So what we have is negative 2x over, let's look at this denominator. This h becomes 0, so this is x squared and another x squared. So we have this, right? And that cancels, so we have negative 2 over x cubed. And since we are trying to get to the power rule, let's just write it like that. So far, so good. Questions now? Okay, then let's just notice a bunch of patterns that we have done. Here's our function, and here's the derivative of that function. I will make a little table here, okay? We have done this, I think. I mean, it's obvious. Constant function, that becomes 0, right? Let's skip the constant function. Mx, that's m, right? The slope. You see it, even if we do difference quotient, we'll just get the slope of that line. And we have done this, and derivative was this. And we have done this, and derivative was this. And we have done this, 1 over x, right? And the derivative was this. And today we have done this one, right? 1 over x squared, and derivative is this. Are we seeing a pattern here? We have even done this, square root x. And what was the derivative? We even done this. And that derivative was. So those of you who don't know what power rule is yet, do you see the pattern? If I write x to the, let's say, 7, somebody tell me what that derivative should be.
6.
7x to the 6. You see what's going on? The power moves front. If I have x to the pi, actually that's like not easy to believe, but it's this. It still works exactly the same way. So here comes the formula then. X to the n's. And that should be n, x, and minus 1. And n does not need to be an integer here, as you can see here in 1/2 power. And pi, we haven't seen this. This actually requires a little more to prove it. Are you a believer now? No, you should not believe so easily. At this level, you should demand the proof. Okay? So let's do the proof of that. I'm gonna do that into x. So we are going to differentiate x to the nth power. Now here's a little disclaimer. This only works for polynomial looking thingy. For example, as soon as you write something like this, see there's no power anymore. You can't do it. It doesn't work. Okay? So that's a disclaimer. Only works for polynomial or like some x to the something power. And another thing, this proof is only limited to integer n. Actually, it's more like natural number n. General proof, you don't really have what it takes to understand it. You have to wait until chapter 8. So I just prove it for integer n, and you're going to have to trust me. Let's do it according to the definition. It's x plus h to the nth power minus x to the nth power over ha. Then, do you know how to expand binomial? Pascal's triangle, binomial theorem. It goes like this. And then it's combination of n, choose 2. And then combination n, choose 3. And then we'll go dot, dot, dot. And then h to the nth power. And then finally minus x to the n, last step. You with me? Then this thingy and this thingy cancels. Now, once you cancel it, do you see everything else has h in it at least once? Factor it out and cancel this denominator h. So what we have is h approaching 0 of, not to forget parentheses, like that, eh? Now, we take the limit and h dies. So lo and behold. Wow. So now I hereby relieve you from this burden of using difference quotient, and you can do homework like this. Unless I ask you for the definition of the derivative on the test, and we are still evaluating that limit difference quotient. But for example, suppose we have a function x to the fourth power minus 2x third power plus 5x squared minus 7x plus 3. Okay, now we can just evaluate the derivative like this. This 4 comes to the front for x and you subtract 1. Now this one comes to the front, but are you convinced that we can just multiply? Like that? Good. And then we have 10x to the first power. And this is 1 here, so we have minus 7x. And that's it. What? Oh, not 7x, just 7. What? And then what happens to this 3? It dies. But do we have to memorize the constant? What's the slope of constant function? It's 0. But let's not memorize it. Let's think like this. That way, this is 7 to the 0 power, which is 1. And that you multiply, that's why it becomes 0. You get it? So this is consistent. However, that's extra writing. So in reality, we stop right there, knowing 7 times 1 is still 7, and then the other one is 0. You get it? Okay. And then there is something called the product rule. Fancy writing, right? Product rule. Now I have a question. And the question is this. If my function happens to be something times something else, is my derivative, is it equal to maybe 2x, the derivative of the first term, times the derivative of the second term? What do you say? Could that be true? Because as you can see, derivative of something plus something is a derivative. You know what I'm saying? And also, limit of something times something is limit something, limit times limit something. So in this case, is it derivative times derivative? What do you say, people? Is it true or is it not true? Don't you wish life was that easy and simple? Right. No, 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 no. See, whenever something seems to be too good to be true, then it always is. Here's a one easy way to verify it. We'll multiply this out. Oh, by the way, the term FOIL is not really mathematical vocabulary. Okay, it's just something that middle school books invented as an acronym. So this is 2x to the fourth power plus x squared minus 3. Too much algebra? No. So f prime of x, we just know how to learn how to do this with a power rule. 8x cubed plus 2x and everything else is 0. And then these two are not the same. You know what I'm saying? So no, no, no. Okay, then that's too bad. I'm going to teach you how this product rule works with this example. Then I'm going to prove it. So here comes the product rule. Derivative of u as a function times v as a function. Close the one. Here's a nice abbreviation. This computer is really laggy today. Get it? For some reason, your book puts this thing backward, like v u prime. Like, that's stupid because we have something called quotient rule. This is a better pattern. Okay, so keep it like this. Okay, so let's learn how to use it, shall we? This function right here is u. First thing, x squared minus 1, and this is v. So I'm going to do f prime of x here is, now first we have u prime v. So derivative of that thingy, which is 2x times v. Good. And then we have u v prime. So this thingy, so plus x squared minus 1. And v prime is 4x. Okay, just to verify, we're going to multiply this out. So we have 4x cubed plus 6x plus 4x cubed minus 4x, like terms, 8x cubed plus 2x. And that's exactly the same thing as this. You see how the product rule works? Okay, then, shall we prove it? Yes, we shall. Because you should demand the proof at this level. Just because your teacher said so does not make it true. I rarely say this is what it is and memorize it. Okay? So let's say derivative of u function of x times v function of x, and we are going to differentiate it using difference quotient, of course. This is u of x plus h. Now v of x plus h minus u of x v of x all over h. Good. You see why it's not going to work out to be so nice, eh? Okay, this is equal to limit of h approaching 0 of u of x plus h, v x plus h, space, I think I need about that much space, minus u of x, v of x. Is this still exactly the same thing as before? Okay, but whenever the teacher leaves that much space, he's going to put something in it, right? And in it, I'm going to insert this. It's really a trick. It's not like I expect you to come up with this out of the blue thin air. Exactly the right amount of space. What have I inserted and why can I justify this action? I have inserted 0 in the middle of an expression, so it's exactly the same as before, right? Okay, now, but then we have limit of h approaching 0. Now let's see if you agree with this. I have a common factor here and here. I'm going to factor that out. So I have u of x plus h minus u of x over h. And then I'm going to put v of x plus h out here. So let's see if it's really the same thing as the first term, right? This half of it. If I distribute this, I get exactly the same thing, right? Because we multiply to the numerator of a fraction. And likewise, I have u of x as a common factor, right? So u of x here, and then I can have v of x plus h minus v of x over h. Still with me? Now limit, 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 limit. Oh, there is a pretty neat thing I can do with, since this is distance learning. Let's see, let me try this skill. Okay, it was not as dramatic as I wanted to be. Do you see what I'm getting at? Of course, this does not work when I need it. It could have been a little smoother, but hey. So this is limit times limit of this term plus limit of this term times limit of this term, isn't it? Property of limit, limits distribute and just take a limit of everything. Now, tell me what this first term is. That's u prime of x, isn't it? That's the difference quotient as we know it, right? This second one, this h dies, right? And then this. So that one just becomes v of x. Good. And third one, there's no h in it, so this thing does not affect the function. And then last one here, this is the derivative of v. What do you have? We have a product rule. You get it? Likewise, we have something called the quotient rule. Okay. Quotient rule. I'm going to write down quotient rule here on the side. U over v. Derivative is u prime v minus uv prime over v squared. Oh, ugly, ugly. Yeah, this is like, I dread this quotient rule. What time does this period end? 5 minutes. Plow through? I think I can make it. Okay, so if we want to take a derivative of u of x over v of x, and that is limit of h approaching 0 of u of x plus h over v of x plus h minus u of x over v of x all over h, eh? Now we have fraction. Whenever we have fraction, what do? Common denominator, of course, like we did earlier. Okay, so we are supposed to multiply this upward that way and that way, right? So we have u of x plus h minus v of x, or minus times, pardon me, times, really, v of x minus u of x, and then v of x plus h, right? And that 1 over h, we can just stick h in here. Okay, that thingy is exactly same as, oh, by the way, if you have to leave, you may go u of x plus h, v of x, about that much space, minus u of x and then v of x plus h, about that much, over h. You with me? Okay, now the same trick applies. So I'm gonna minus u of x, v of x here, and then I'm going to put plus u of x and v of x here. So once again, I only inserted 0 to this expression, but I'm gonna rewrite it. So limit of h approaching 0 of the first term. See, like before, I have u of x. You know what? I forgot that's denominator. Okay, there. So I have this v of x as common factor. So I'm going to factor that out. So I will have this. I'm going to write it like this, and I'm going to write this one here, and then I'm going to put that denominator here. Okay, so let's see if it's the same thing. If we, of course, it's not the same thing. This is the same thing now. If we distribute this, we get that numerator back and we multiply the denominator, right? Okay, so it's exactly the same thing. Now, and the urge is you want to cancel this v of x. No, don't. We need it. And minus, I'm going to factor out u of x, and while I'm at it, I'm going to put this denominator. And then I will have v of x plus h minus v of x over h. Now, let's just take a look at why this is minus, because I have this minus sign, which I factored out here. So if I distribute negative u of x, this thing becomes minus, that thing becomes plus. All with me? Now we take limit. Don't have time to show you that fancy computer trick. So this first one, is that the derivative of u prime of x times the second one is just the v of x over this thingy is v of x quantity squared, isn't it? This denominator of the second term. Now minus, and then we have u of x over v of x quantity squared, and then times the last term is just v prime of x. Just to make it look prettier by common denominator, well, this is x, v of x minus u of x, v prime of x over v of x quantity squared, which is the quotient rule, as I wrote. Okay, whenever we have that, we can just take the constant outside, then take a derivative. I mean, we've been doing that for some time now. For example, you know, derivative of like 4x cubed. Then we just multiplied it, but technically that's this, isn't it? That's kind of what it means, right? So constants, we just put it outside. But what justifies that action? If you want to do a product rule, this is how you do it. So constant times f of x. And then let's say this is u and this is v. And product rule looks like this. Right? So u prime, derivative of constant is 0 times v plus u, our constant, times that, which just tells you constant times f prime of x now, isn't it? Huh, it proves it that easily. But better version is, why don't we do a difference quotient, eh? I mean, you are not required to do this, but hey, say we want to do this. That is limit of h approaching 0 of c f of x plus h, right? Minus c f of x over h now, isn't it? And then, as you can see, h is a common factor, eh? And then we take a limit of c is still c, eh? And then limit of that thingy, what we see here is our derivative, isn't it? Oh, this would be a much better proof. When in doubt, going back to the definition is always a better proof, but then they say use the product rule, so there's a product rule. How's that? Good? Okay, let's do ideal gas law. PV, do you see PV is equal to nRT, like about there? Right, and all of you took chemistry, so you know what that means, right? Okay. But they are saying T is constant, right? And then pressure will be a function of volume V. This tells you how little these mathematicians know about science, right? That's a very tricky thing to do. How do you change the volume, compress the gas without increasing the temperature of the gas? Like, those are, you can't do that easily. I mean, you can have some kind of freezer to control the, right? Anyway, assuming that is possible, then let's do this. So by the way, let me remind you, quotient rule looks like this. However, this V right here is not the same thing as that V over there, right? So let's not get confused. These are representing functions. So dp over dv now, V is your x, if you will. And then first thing, you see the denominator square is what we get from the quotient rule, right? And then think of this as a u and this as a v. So u prime is 0, isn't it? We are holding that because nr always has been constant from ideal gas law. And then t is constant in this problem. So that's 0 times u minus nv minus, and then u, which is nRT, times derivative of this denominator. Isn't that just 1? Say yes, because nb is constant, which dies in differentiation. Okay, and second part, of course, is this then, right? And then this, think of this as a u, so u prime, which is also 0, that's constant, times v squared minus u and times derivative of v, like that. And if we simplify, the first part is negative nRT over v minus nv quantity square, and second part is plus minus minus plus a n square v2 in the front over v to the fourth. But think about it, v cancels a, so cube like that. How about that? Good.